Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning. Today we will examine ocean current systems and their role in global circulation and climate. I will discuss the main driving mechanisms, the large-scale patterns that arise, and several concrete examples that show how currents influence regional climate. Begin with mechanisms. Surface currents are primarily wind-driven. Persistent wind patterns push the top layer of the ocean, and, because of the Coriolis effect, water moves at an angle leading to Ekman transport. Ekman transport causes convergence and divergence at the surface. Where wind-driven divergence occurs along eastern ocean margins, we see coastal upwelling. The Peruvian or Humboldt current region is a classic example of this process. Below the surface, we have thermohaline circulation. This overturning flow is driven by density differences due to temperature and salinity. Cold, salty water sinks in high-latitude regions and flows equatorward at depth. The combination of wind-driven gyres and thermohaline processes produces distinct large-scale features. Subtropical gyres form in each ocean basin. Western boundary currents, such as the Gulf Stream and the Kuroshio, are intensified, fast, and narrow. For example, the Gulf Stream carries warm water from the subtropics to the North Atlantic and moderates European climate. This is a clear demonstration of how current systems transport heat poleward. In the Southern Ocean, the Antarctic Circumpolar current stands out as the only current that encircles the globe. It connects the Atlantic, Pacific, and Indian basins and plays a large role in global mixing and carbon transport. Another key example is the Humboldt current off South America. It is a cold eastern boundary current associated with strong upwelling, which supports rich fisheries because nutrients rise to the surface. Interannual variability in equatorial current systems leads to events like El Niño. During El Niño, trade winds weaken and eastward surface waters increase. Upwelling off Peru is reduced and regional climate patterns shift. We must also consider western intensification, a dynamical consequence of the Earth's rotation and basin geometry. It explains why western boundary currents are stronger than eastern boundary currents in the same gyre. On longer timescales, the Atlantic Meridional Overturning Circulation, or AMOC, is crucial. It transports heat northward in the Atlantic and contributes to climate stability in the North Atlantic sector. If the Atlantic Meridional Overturning Circulation slows, the result could be substantial changes to weather patterns in the North Atlantic region. That statement is not speculative. Paleoclimate records show past changes in overturning strength coincided with abrupt climate shifts. Modern observations suggest freshwater input and warming could alter circulation in the future. Measurement and modeling of current systems combines satellite altimetry, surface drifters, and profiling floats such as the Argo array. These tools let us estimate transport, detect anomalies, and validate numerical models. Currents also affect the carbon cycle. By moving water masses between the surface and interior, currents influence the biological pump and the ocean's capacity to store carbon dioxide. In summary, ocean current systems form an integrated global circulation. Wind-driven gyres, boundary currents, and thermohaline overturning interact and determine regional climates, marine productivity, and long-term climate feedbacks. Understanding these systems requires observation across scales and careful modeling. For our next session, we will look at specific numerical experiments that simulate changes to the AMOC and their projected climatic impacts. Thank you. If you have questions about any current system or mechanism mentioned today, please ask now or send me an email.
Listen again to part of the lecture, then answer the question.
If the Atlantic Meridional overturning circulation slows, the result could be substantial changes to weather patterns in the North Atlantic region.
This concludes the listening section. For more TOEFL practice tests and study materials, visit spinta.org.